Welcome to the workshop. We want to continue taking a look at the third section of the appendix on proof methods. We want to introduce a new method of proof called a proof by contradiction. A lot of times in a proof by contradiction, we're not proving a implication or a conditional statement. Rather, we are proving a different type of statement. So if we want to show that a simple statement P is true, then we could do that by a proof of contradiction in some cases. So let's take a look at our notes. So in its most basic sense, if we want to prove that a statement is true by contradiction, what we're doing is we're showing that if something cannot be false, then it must be true. So we suppose that it's false, and when we suppose that it's false, we end up with something that doesn't make sense, and we say, this doesn't make sense when it's false, therefore it must be true. Okay, that's the basic idea. Okay, so what we do for a proof by contradiction of just a statement Q, we suppose that it's not true. This will usually lead us to something, but then using not Q, it'll lead us to saying not that something as well. And a lot of times this something here, this actually appears before that when we're taking a look at some of the basics of the problem as well. So what I mean by that is, let's see here. Actually, this is written as an if-then statement, and that's okay. So what we usually do is we have an S that appears before supposing not Q. So here, this is actually, our example is given as an if-then statement, but we could rewrite it so that way it's not. A lot of times they're written so they're not seen as if-then statements. So if we were to think of this as for A and B positive real numbers, square root of A plus square root of B is not equal to A plus B. So we simply have this statement here, which is our Q. So we can look at this as not being an implication. We can look at this as just being some statement Q, and that's it. And when we do that, we can prove this, again, using a contradiction. This is also very nice when we're trying to prove that something is not equal to, right? Showing not equal to can be a little bit difficult. But if we want to assume some sort of equality, then we can start making manipulations on both sides of the equation. So this would be a good case for us to use by contradiction. Another way that might be, right, negating Q. Another situation in which we would negate Q is by contraposition. But looking at it this way, we don't have an implication. Implication would be for would be needed for us to talk about a contraposition or contrapositive. All right, so let's see here. Yes. So a proof. So whether we're considering this an if-then statement or just Q, it's the same approach either way. So let's approach it like it's written here. It's adjusted. That's okay. It's not a big deal. But what we want to recognize here is that with it written this way, with these adjustments, this is not an implication. Not an implication. With these adjustments. Excellent. So with it like this, so again, what we'd like to prove is we would like to prove for positive real numbers A and B, we want to prove that, let's see here, the square root of A plus the square root of b is not equal to the square root of a plus b. Okay. So that should look like square root a plus square root b is not equal to square root of a plus b. So for these, let a and b be real numbers, then these are not positive real numbers, then they are not equal. So if we wanted to prove this proof, we would say let a and b be positive real numbers. In this case, that is a is greater than 0 and b is greater than 0. Okay, they're real numbers that are greater than 0. Excellent. So suppose for a contradiction that we have equality, right? So we have not equal to, that is equal to. So suppose for a contradiction that they are in fact equal to one another. Okay, what does that give us? Well, we're not going to know immediately where this is going to go, and that's fine. But what can we do to this? Well, we know that a is greater than 0 and b is greater than 0. So let's see what we can find out about a and b when we say that these are equal to one another. So this would give us, let's say we square both sides. That would give us a plus 2 times the square root of ab plus b is equal to a plus b by squaring both sides. Okay, cool. Well, now there's an a and a b on both sides, so I can get subtract that from each side to get 2 times the square root of ab is equal to 0. Well, what does that do for us? Well, now I have an equation equal to 0, and it's just a bunch of factors. Well, I suppose I have a square root here. So what I can do is I can pretty easily solve for a or b in this case. I can divide both sides by 2 to get square root of ab is equal to 0. Then square both sides to get that ab is equal to 0. And by the zero factor property, we would say that a is equal to 0 or b is equal to 0. Does that make sense? No. So we have, hence, a is equal to 0 and a is greater than 0, right? A is greater than 0 and a is equal to 0, or b is equal to 0 and b is greater than 0. But we can't have a equal to 0 and be greater than 0, and we can't have b be equal to 0 and be greater than 0. So this is a contradiction. Contradiction. So if we have a contradiction, that means, right, we have an impossible situation. This cannot happen. We cannot have that a is equal to 0 and greater than 0. We can't have that b is equal to 0 and b is greater than 0. So it doesn't matter which one we're talking about. We're saying one of these two things has to be true, but either way you go, it's a contradiction. It can't happen. So since this can't happen, then what we supposed for a contradiction must not be true. So therefore, the square root of a plus the square root of b cannot be equal to the square root of a plus b. And that's it. That is a proof by contradiction. Excellent. So that's all that I wanted to share in this video. So I'll see you guys back in the workshop in a little bit.